So after stating the problem we wanted to solve, I will present related results and how this work connects to previous results, and then I will mention some facts about estimation of unitarily invariant properties, which are useful for our problem. And finally, I will give some ideas on how we prove the upper bound on the sample complexity and the lower bound on the sample complexity. And I will finish with some remarks. Okay, so we consider a sampling model where we have access to copies of this classical quantum state rho, where the states rho I are a collection of unknown d-dimensional quantum states. There are n of them, in principle different. And the pi is a known probability distribution. And the cats I from 1 to n form an orthonormal basis of Cn, which is also assumed to be known. So this model should represent a situation where we have, for example, a quantum device which produces some quantum states at the end of a probabilistic process. And we get a flag telling us the outcome of the process, which is associated to a specific quantum state. We are interested in understanding whether the source is stable, that is, it produces always the same state or not. Let me be a bit more formal on the problem we want to address. So we are promised that one of the two following properties holds. Either we are in case A, where all the states of the collection are equal, or we are in case B. That is, for any d-dimensional state sigma, it holds that the average of the trace distance between the states of the collection and sigma is larger than epsilon. The task is to design a two-outcome test that uses m copies of rho, which can return either accept or reject, and which accepts with probability larger than 2/3 in case A, and it accepts with probability smaller than 1/3 in case B. The goal of our analysis is to find necessary and sufficient values for m such that the test exists. And the sample complexity of the problem is determined if the upper and lower bounds on m have the same dependence on n, d, and epsilon. Let me make some remarks here. So the task is indeed an example of composite hypothesis testing, where the states are promised to belong to one of two sets of state. But in this case, our attention is focused on finite size effects following the approach of quantum property testing. And in particular, we do not aim at optimizing the asymptotic error rate. And we care instead, as I already said, about the dependence on the sample complexity on the parameters of the model, so n, d, and epsilon. It is important to remember that in these cases, the probability of success can be amplified from the 2/3 that I used to any probability of success 1 minus delta by multiplying the number of copies by the logarithm of 1 over delta. Okay, what are the related results in this area? Maybe the most important paper is the paper by Badescu, O'Donnell, and Wright, which deals with testing identity of two unknown states. So they find with two states and equal fixed number of copies of each, that the sample complexity is d over epsilon square. I will refer to this paper as BOW in the following. There is another paper about testing identity of collection of quantum states which deals with the query model, where one has the freedom to choose which rho I to receive. And our setting is alternative to that. In the query model, the sample complexity is again d over epsilon square. These problems have also been considered in the classical case, where the sample complexity of identity testing for two unknown distributions is this expression here, which is a bit more involved with respect to the quantum case. And the problem of testing identity of collections of n distribution has been solved both in the sampling model and the query model. And again, the query model has the same sample complexity of the case with just two unknown distributions. Instead, in the sampling model, we see that the sample complexity is worse, and in particular, in the part that depends on epsilon square, we see that the sample complexity is worse by a factor square root of n. So in our work, we find these upper and lower bounds on M, which combine the methods of Bow and the ideas also of the paper that address the classical case. And indeed, what we find is that the sample complexity for identity testing of collection of states in the sampling model is square root of n d over epsilon square, which was somehow expected. This can be compared with doing tomography. For example, if the probability distribution is uniform, then one can do tomography of all states rho I with a number of copies that scales like n d square over epsilon square, disregarding logarithmic factors. And our tester does much better than that. Okay, so these are the statements of the theorems that give us the upper and lower bound, which indeed match. Okay, before going into details of our proofs, let me say something about the estimation of unitarily invariant properties to frame this problem in a much broader context, which is interesting. And it is also useful to state these things to understand better the ideas behind the proofs. So every time we have a product of multi-copy states, where we have a collection of states appearing a certain number of times, each state appearing a certain number of times, then we may be interested in estimating properties which are invariant under change of reference frame. And we model these quantities as unitarily invariant properties, such that they are invariant under the action of the tensor product representation of the special unitary group. Examples are the spectrum of each rho I and their functions, so the purity, the von Neumann entropy, the spectrum of convex combination, the distance between the states, but also the property of being in case A for a collection of states, and the property of being in case B, and many other interesting things. The nice thing is that optimal measurements for estimating properties which are invariant under the action of a group can be characterized with the help of symmetry principles. And for reasonable figures of merit, the POVM, optimal POVM can often be chosen to be invariant. That is, it is invariant under the action of the representation. And this means that the elements of the POVM has to obey selection rules, and therefore they are easier to characterize. So in particular, for multi-copy states, the relevant group is SUD times Sn, where Sn is the group of permutation of an object, if we have n copies of a state. And specifically, this group acts with the tensor product representation of SUD, and the permutation part simply permutes the Hilbert space of H tensor n, well, according to the given permutation. It is an important result that H tensor n can be decomposed according to the irreducible representation of the representation we just recalled, and this result goes under the name of Schur-Weyl duality. And so H tensor n can be written as a direct sum of spaces hosting irreducible representation labeled by partitions of n with at most d parts. which are pictorially represented by Young diagrams. So the projectors on the spaces in this direct sum form a projective measurement called Wicksure sampling. And this measurement is efficiently implementable on a quantum computer. It has gate complexity that goes like n log d log 1 over delta, where delta is the precision of the implementation. Now, the average of the tensor product representation of SUD on a multi-copy state gives a state which is a convex combination of completely mixed state on the Hilbert space, on the sectors hosting the reducible representations, weighted by the Schur-Weil distribution of rho, as it is defined, as it is called, which depends only on the spectrum of rho. And indeed, the optimal measurement for estimating the spectrum of rho is Wicksure sampling. And the probability of finding the label lambda is given by the Schur-Weil distribution. If we then take the estimate lambda bar, which is the vector of the partition normalized by n, we get a good estimate for the spectrum of rho according to this exponential concentration. And in fact, bar lambda gives an accurate estimate of the spectrum in total variation distance with d square over epsilon square copies. Okay, now I'm ready to go to our original results. And let me start by summarizing the proof steps for the upper bound. So first we look for an unbiased estimator of this quantity, the mean squared Hilbert-Schmidt distance between the states of the collection. We find a bound on the variance of this estimator for a large number of copies mu. I will explain in a moment why I will use mu and not m. And thanks to a modified Chebyshev inequality appearing in bow, we can adapt their argument and find, and using this bound on the variance, to find an upper bound on the complexity of testing identity of the collection with respect to the Hilbert-Schmidt. So the mean squared Hilbert-Schmidt distance. And then we find an upper bound on the complexity for the original problem via an inequality connecting MHS with the average trace distance with respect to the average state, which is simply defined here. So how do we build our estimator? Okay, so we care only about the number of copies each state appears. So if we have m1 copies of rho 1 in a certain sequence of states that comes from m samplings of the original source, then we rearrange the sequence in order that the first m1 states are rho 1, and then if we have m2 copies of rho 2, they are just after the copies of rho 1, and so on. And so we save only the information about the number of copies in this vector m, which is distributed according to a multinomial distribution. The starting point for the estimator is the unbiased estimator for the Hilbert-Schmidt, squared Hilbert-Schmidt distance of rho I and rho j from mi copies of rho I and mj copies of rho j, which was found in bow. And this is a linear combination of these operators, which are remission operators corresponding to the average of all possible different transpositions, swapping one of the states rho I with one of the states rho j, with I and j possibly equal. And we can compute expectation value using the fact basically that the expectation value of a swap for a product of two, for a tensor product of two states is just the trace of the product of the density matrices. And we can also evaluate expectation values of products of these operators O, I, and J. The problem here is that Mi are correlated random variables in the sampling model. Therefore, it is a complication in the calculation, and it is easier to compute. So to prove the upper bound by getting rid of correlation between Mi, and the trick is to use Poissonization. Instead of having a fixed number of copies of the original source, M is instead a random variable which is distributed according to a Poissonian distribution with average mu. And in this way, we see that the probability distribution of the vector M of number of copies is in fact factorized, and the variables Mi become independent, and each Mi distributed according to a Poissonian distribution. And this makes the calculation much simpler. Nice thing is that the Poissonian sampling model can be simulated with the original model, and one can do it in this way. One takes from the original model M equal to mu, samples M prime from the Poissonian distribution, and if M is larger than M prime, one can continue. Otherwise, one declares failure, and the failure probability is small because of the exponential concentration properties of the Poissonian distribution. Okay. So with this trick, we are able to find a good observable, which of course we have. So of course we have a different observable for each vector M, and which depends explicitly on the vector of number of copies, but this is in fact an unbiased estimator if in the Poissonian sampling model, and it is a good choice since it has a bounded variance in the way that I was telling before. We know also how to implement the observable, and this can be done by writing the observable in this alternative way, where now the operator O is the average of all transposition on H tensor M, which is implemented by global mixture sampling on all the M factors. And O can in fact be written in this way, as a linear combination of mixture projectors. But this is also obviously true that even all the OII can be implemented by local mixture sampling. That is mixture sampling only on the states with label I. And since these local mixture samplings and the global mixture sampling commute, then we can find an implementation of the observable that we call nested mixture sampling. And the way to describe this pictorially is the following: all the states with the same label undergo non-destructive local mixture sampling measurement, and the post-measurement state are then sent to a global mixture sampling measurement, and all the labels then get post-processed to obtain the estimate that we are looking for. And of course, this secret is also efficiently implementable since each of these blocks is efficiently implementable. Okay, now I can also give some details, some ideas on the proof of the lower bound. Here, the idea is the following. So we look for two sets of collections of states which satisfy case A and case B respectively with high probability. If a good test exists, then it can distinguish between the average input states of the two sets. So the first set is very simple. It contains only the collection, the collection of maximally mixed states. And of course, the average states just corresponds to m copies of the state row corresponding to the collection of maximally mixed states. So the set B contains instead all the collection of states with half of eigenvalues equal to 1 plus 8 epsilon over d, and half equal to 1 minus 8 epsilon over d. And yes, we also consider the probabilities to be uniform because we are interested in a worst case scenario, and this is a good choice. So the average state in this case is given by this rho B, where the average is done over the R random, over the R measure of SUD, and each state of the collection is obtained by applying a random unitary to rho 0, which is a state with the spectrum that we desire. And it can be verified that these states with this probability distribution associated to the collection satisfy case B with high probability. Then we just need to bound the distinguishability of rho A and rho B. And this can be done since both states can be written in terms of the Schur-Weil distribution of the maximally mixed state and of rho 0. And so we can use bounds on the chi-square divergence of Schur-Weil distribution obtained in this paper. And we find that the trace distance between rho A and rho B is upper bounded by this quantity. And in order to be large enough such that it is possible that the test exists, m has to scale like square root of n d over epsilon square. And so this gives the lower bound. Okay, so now I'm ready to finish. Let me just state again the result. The sample complexity of testing identity of collections of quantum states in the sampling model is square root of n times d divided by epsilon square. The measurement implemented in the test is computationally efficient. We also have this result that I didn't mention, but it's easy to obtain, that when the rank of the average state is approximately k, the test can be done with square root of n k over epsilon square copies. And there are related open questions. It would be nice to have a better analysis for fixed probability distribution, since we assume that we know the probability distribution. But it will be also interesting to understand the case where we don't know the probability distribution, and maybe we don't know the basis in which the classical quantum state. So the basis of the classical register of the classical quantum state, which would be equivalent to testing independence of unknown classical quantum states. And about testing independence, it is also true that the problem of testing independence for general multipartite quantum states is still open, although in this paper there have been several advancements. And this problem is also interesting in the asymptotic settings, and see also this other paper here. So with this, I have finished, and I thank you for the attention.
So thanks a lot for the talk. Are there any questions? So either unmute yourself or in the Slack or in the chat. Okay, so I'll start with the question. So first, so is there a condition on n and how it relates to d here?
No.
Or, no, so n can be arbitrary. It can be much larger than d.
Yes, exactly. Yes.
Okay, and another question I had is, now what if you limit yourself to a measurement which is limited, like let's say product measurement. Okay, let's say the simplest setting where it's product measurements and non-adaptive at all. Do you know how the complexity changes?
Yeah, I think that yeah, in the sampling model, I think that there is nothing, but maybe in the query model there is something in this paper.
Okay.
And I'm not sure, but no, I cannot say anything now. Thank you for the question.
Other questions? Okay, so then let's thank Marco again, and let the next speaker set up, and we'll start in 2 minutes.
Hello, can you hear me?
Yes, we can hear you, but can you share your screen?
Yes.
Now you should be able to do it.
Okay. Are you seeing something now?
Yes, now we can see your screen. Perfect.
Okay, now should be presentation mode.
So we can hear you, but the sound is a bit low. Can you?
Now better?
Now it's better. Yes.
It was my voice that I was.
Let's wait just 1 minute and then start. Okay, good. So the next speaker is Josep Lumbreras from Singapore, and he will talk about quantum bandits. Please go ahead.
Okay, thanks organizer and the committee for the opportunity. Yeah, I'm going to present the problem of multi-armed quantum bandits. It has been a joint work with Dr. Erka Hapsolo and Professor Marco Tomamichael. And well, if you are interested, here you have the archive reference. Okay, let's start. First of all, I will review the multi-armed bandit problem. It's a classical problem. So I will start with an example. Suppose that we are in a casino and we have some of these slot machines, and we want to detect the slot machine that gives us the highest reward, because each of these slot machines follow a slightly different probability distribution. So the thing that we want to do is we want to explore all these slot machines, so pulling the arm and observing the rewards. But at the same time, we want to exploit the slot machines that apparently give us the highest reward. So this is a trade-off in this learning problem of exploration versus exploitation. So we want to explore all these slot machines, but at the same time we want to explode those ones that give us the highest reward. So more formally, we can formulate the multi-armed stochastic bandit problem as follows: is that we are given a set of unknown probability distributions to a learner, xi from 1 to k, and we have a learner that over n rounds interacts with this probability distribution. So it selects one of these probability distributions and samples a reward. And what the objective of the learner is to maximize the total cumulative reward. So this is one of the simple model of decision making with uncertainty. And as I said before, it's a trade-off between exploration and exploitation. And there are a lot of practical examples. So one can be, for example, slot machines, or you can, for example, model as a bandit problem of restaurant selection. So, for example, you want this night I want to go to dinner to some restaurant. So I know some restaurants that are good, so I can explore those ones, or I can explore to some unknown restaurants with the risk that maybe they are better or maybe they are worse. So yeah, there's just a few examples. We have extended this this stochastic bandit problem to a quantum learning scenario, and this is the multi-army quantum bandits. And the model is described by two things. One is a set of quantum states that we call the environment, and the other one is the set of observables that we call the actions. So the observables are just Hermitian operators, and we define two types of bandits. One that are with discrete and finite action set. So this action set is just a finite set of observables, or a bandit with continuous action set that are action set that contains, or for example, a particular example is, for example, a set of all rank 1 projectors. So the bandit problem is characterized by the tuple of actions and environment. So thing to remember here is that actions are observables and environment are a set of quantum states. So how the learner interacts with the bandit, it goes as follows. The learner will interact over n rounds with the environment, so with a known quantum state from this set of quantum states. What we'll do is, at each round, the learner will select one observable from the action set and will perform a measurement on the known quantum state. And from this, we'll sample a reward with the probability distribution associated to the quantum state and the observable. So this strategy is of the learner is determined by what we call a policy, and a policy is just algorithm that tells you at each round what observable to select. So you will be selecting observables and sampling rewards, and from this information, the learner is the information that the learner will use to decide which observable to pick next. So this is how the learner interacts with the bandit. Now, what is the objective? Well, this is a scheme of how it works. So yeah, the learner uses the past observations in order to decide the next observable to pick from the action set. So what is the objective of the learner? So the learner wants to find the action, so the observable in the action set, that in expectation maximizes the reward. So this means that it wants to find the observable that has maximum overlap with the unknown quantum state. So this is equivalent to minimizing the expected cumulative regret, that is the following expression that we have here. That is just a sum over n rounds of the relative loss, that the relative loss is defined as follows, is just the difference between the maximum expectation value that we can have. So it's a maximization of the trace of the non-quantum state and maximization over all the observables in the action set, minus the expectation of the trace of the non-quantum state and the observable that is selecting the learner at round t. So here there is we have to take into account that this observable is a random variable since it's the choice of the learner. So this is determined by the strategy. So that's why here there is the expectation value here. And special cases of this regret is, for example, if the action set contains all rank 1 projectors, minimizing the regret implies finding the maximum eigenvector of the unknown quantum state. Or more specifically, one of the cases that we study is that if the unknown quantum state is also pure and the action set contains all rank projectors, then the regret can be expressed as follows. That is the sum of from 1 to n of the expectation value of this is the trace distance between the unknown quantum state and the rank 1 projector, trace distance square. So minimizing the regret implies minimizing this trace distance. In this can be seen as online quantum state tomography with minimal regret. So the regret that I explained before is just for a particular state, but we're interested in the following regrets. That is, one is the worst case regret that has the following formula that is given a set of density matrices, that is the environment, is just the worst case regret, which means that is the supremum of the over all possible regrets, or the supremum is taken for the unknown quantum states in the given set. So this worst case regret, it tells us how well a policy, so a strategy for the learner, performs for the given set of unknown quantum states, so the environments. So, and then the minimax regrets is defined as the best thing that that can achieve a policy over all these worst case regrets. So it's a minimization of the worst case regret over all set of policies or over all set of strategies. And the minimax regret is it tells how difficult is the problem given by a set of environments in a worst case scenario. So,
a quick question here, maybe.
Yeah.
How can we see, just to get used to the notation, how can we see the classical case you mentioned at the beginning as a special case of this? Can you say what rho is and what the
yes, sure. So here, in the classical case, what you have is probability distributions, no? So the regret is just the difference between the best, say the highest mean of this set of probability distributions and the mean of the probability distribution that you are playing at this time step. So the analogous will be that, for example, the rows is just, for example, a possible set of probability distribution that, for example, can be Gaussian distributions or whatever, and the actions is just a set of indices that tells you which action to pick.
Okay, great, thanks.
Yeah, so what we have to keep in mind is that the formality regret is just the relative loss between the expectation value of the best thing that you can do, so the best observer that you can choose, and the one that you are choosing each round. So, and this minimax regret is, as I said before, it tells just us how well performs a policy for a given problem. That, remember, the problem is given by the set of actions and the set of environments that actions are observables, and the environment are the set of quantum states. So the goal of this work is to give bounds on this minimax regrets for different set of environments or quantum states and set of actions, so observables, in terms of the number of rounds n, so the number of rounds that the learner interacts, and the dimension of the Hilbert space where the quantum state and the observable lives. So we differentiate between lower and upper bounds. So for the lower bounds, we will use an information theoretic techniques to derive the lower bounds. And for the upper bound, we'll find algorithms and we'll analyze the regret. Yeah, so I started describing the general case where the environment, so the set of unknown quantum states, we let that this be to any quantum state. So it's just a set of mixed states for a given dimension D. And the action set, we consider a finite set of observables. So from observable 1 to observable k. Note that if we don't impose any condition on the action set, we have a trivial lower bound. Why? Because there is, for example, a simple example that if the action set is only, there are only two observables, and one is bigger than the other in a metric sense, then we have that for any quantum state rho, the expectation of one of these observables will be always greater than the other. And this implies that since the minimax regret is a minimization over all policies, there is always a policies that choose as action the observable one. So the regret will be always zero because we are always choosing the best action. So in that case, we define what we call a dominating condition. That is that we say that an observable is dominating in action set if the overlap of this observable with its maximal eigenvector, so the eigenvector of this observable with highest eigenvalue, is always greater than the overlap of this maximal eigenvector with any other with any other observable of the set. So the first result that we have is that if we consider discrete multi-armed quantum bandit, where we let the action set is discrete and the environment is any quantum state, then for d greater or equal to 2, if the action set is comprised of traceless observables and contains at least two dominating observables, we have the minimax regret scales with a lower bound of square root of n. So now I will give a very brief sketch of how we prove these lower bounds just for this case. Every case has some specific calculation, but you can go to the paper to see this. So I will give just an idea. So for the proof of the lower bounds, we use the following inequality, that is the Bretagne-Haber inequality, that tells us the following: that if we have two probability measures, P and Q, on the same irreducible space, and we have an event on this space, that's an arbitrary event, then we have that the P of A plus Q of the complementary of this event will be always greater than 1/2 of the exponential of minus the divergence of these two probability measures, where the divergence is just the standard Kullback-Leibler divergence, so classical divergence. So how the proof works? So we need to find environments, so quantum states that we know that for every policy will perform bad. And we propose two of these quantum states. So in order to do that, what we do is we pick. We have in the conditions of the theorem that there are at least two dominating operators. So we choose from these two operators. We choose their maximal eigenvectors, and we will propose the following quantum states that are just a mixture of the identity operator plus some perturbation of these maximal eigenvectors, and this parameter will be fixed later. For the moment, it's between 0 and 1. And then the regret that I showed you at the start can be reformulated as follows. Now, instead of being a sum over all rounds, it's a sum over all possible indices on the action set. So if we have k observables, it's a sum from 1 to k of the expectation of the number of times that we have played each observable up to RAM n. So this first term is just, it tells us the expectation of the number of times that we have played observable I up to RAM n. And then this is the relative loss between the best action and the observable. Actually, this T should be an I. So it's the relative loss between the observable I and the best observable. So with these things, choosing carefully two sets of indices of the set of observables, we can bound the sum of the two regrets for the two quantum states that I showed you before as proportional to n the parameter delta, and the probability. Well, now we don't have to go into this, but the probability of two complementary events. So since we have that, we can apply the Bretagne-Haber inequality plus data processing inequality to go from a classical divergence to quantum divergence. And in general, we have that the sum of the two regrets is bounded by some constant that depends on the action set, and delta, and the exponential of minus n, the quantum divergence of the two quantum states. And then the proof is completed just seeing that this divergence is greater, I is less or equal than something that goes as delta square, and then choosing delta as 1 over square root of n, the proof is complete. So this is the only proof that I will discuss in this talk. So the other examples that we study work in a similar way, how they are proven. So for example, then we study some specific cases. So this case is a case where, again, is a discrete multi-armed quantum bandit. But in this case, the action set is just a Pauli observable. So we allow that the action set, the set of observables, has k different Pauli observables, and then we can bound the minimax regret as follows. So as before, it goes as square root of n, but now we can introduce the factor that goes as k minus 1. So where k is the number of Pauli observables. So k minus 1 is natural because if we have only k equals to 1, so only one observable, there is only one action, so you are always to pick the right one. So this is why this minus 1 comes from. And then instead of considering, we study also action set that instead of being discrete action set, we allow continuous action sets. So in particular, we allow that the action set consists of all rank 1 projectors in the dimensions. And here we can show that the minimax regret scales as square root of n with a lower bound. So now I'm going to discuss the upper bounds. So for this, we use an algorithm. So now we will discuss the algorithm that can achieve this scaling of the regret. So in order to do that, we work on our vector representation of the quantum state and observables. So using orthonormal basis for Hermitian matrices, we can decompose the quantum states on the observable as follows: that it can be solved just as the inner product of a real vector and the set of Hermitian matrices that are this sigma I, that from 1 to d squared, where d is the dimension of the Hilbert space. So now the mean of each action for the quantum states, we associate the vector zeta, and for the action OI, so the observer OI, this vector AI. So then the trace of rho OI can be seen as just as the inner product of zeta and the and AI, so the vectors associated to rho and the observable. And how the algorithm works. So at each round T, after observing the rewards, so that are sampled from the interaction of the observable with a non-quantum state, after observing the rewards and the observable that we have played, we can approximate the vector that encodes the known quantum state with a least square estimator. So, well, this formula is just the formula of least square estimator for the vector zeta at round T. So, but what the algorithm does is it uses this estimator for the vector of the non-quantum state, and it builds a confidence region that it actually is like an ellipsoid, and would tell us that in this ellipsoid with high probability we will find the real vector that encodes the quantum state. So, and it's centered in this least square estimator. So what does the algorithm does a very simple thing. So at each round it constructs a confidence region for the unknown vector, and then from in this confidence region it finds like the it finds the vector zeta that maximizes the inner product over all possible actions, and then the algorithm selects the best action of this maximization, and will play the observable associated to this action and observes the reward. So this is just an adaptation of the classical algorithm LinUCB for classical multi-armed stochastic bandits. So it's just an application of the classical algorithm, and the scaling that achieves is a scaling that goes as square root of n, and d squared, the dimension, and logarithm of n. So one question that we have here is can we find a quantum version of this LinUCB algorithm, for example? Because this is just an adaptation of the classical problem. So actually, this is a table of our lower and upper bounds. So for a discrete case, we can match lower and upper bounds. So they scale always as square root of n, and we differentiate between arm limited and dimension limited. Unlimited means that the number of observables is less than the dimensional square, and dimension limited it means that we allow a arbitrary number of observables. So the scaling goes, for example, for arm limited as square root of kn, and for dimension limited d square root of n. So in this case, we can match lower and upper bounds almost optimally. There is some logarithm terms, but where we don't have perfect matching is in the continuous settings, where the observables are all rank bound projectors. Since our lower bound goes at the square root of n, and the upper bound goes as d squared square root of n. Actually, the algorithm that I explained is LinUCB, but there are some variants of LinUCB that we apply to the discrete case in order to match the lower bound, but they are similar algorithms. Just to apply to these specific cases. So, yeah, now I will briefly review the other environments that we studied, because now we have studied environments or non-quantum states that can be any possible quantum state, but then we focus on pure state environments. So now the environment is just the set of pure states. Yeah, one result that we have that, for example, for the simple case where the environment are just pure states in a two-dimensional Hilbert space or in qubits, and the action set is just the polymetrices. Well, we don't have anything surprising that the minimax regret, the lower bound scales as square root of n. But what happens is that if we study the same problem with environment of pure states, but the action set contains now all rank 1 projectors, then I explained before the regret can be expressed as the sum of the square of the trace distance between the non-quantum state and the state that you select at each time step. But here we are unable to prove a non-trivial lower bound in this case. So for this case of pure state environments and all rank 1 projectors as the action set, we consider the trace distance regret. So it's the sum from 1 to n of the expectation value of the trace distance between the non-quantum state and the action. So here there is not a square. In this particular case, the lower one that we achieve is it goes as square root of n. But here we have to be careful because now this is no longer the same regret as before. So is this regret that we introduced that square roots in every term. So it's this trace distance regret. And yeah, now for finishing, just if we try to apply the same algorithm that I explained before, LinUCB for this specific case of pure states, the analysis shows that in the trace distance regret, the scaling goes as n3 over 4. So it doesn't match this previous lower bound of square root of n that I show. So, but actually, if a simple variant of tomography achieves a better regret of n that goes as n to the 3. And yeah, this is a sample. This is very simple variance tomography because the only thing that we do is that we base this algorithm in the project least square estimator, that is this paper that fast state tomography with optimal bounds. And this algorithm is very simple. It has only 2 parts. During the first n to the 3 rounds, it just performs polyobservable measurements of the non-quantum states. So here we don't care about exploring or exploiting. We only perform measurements. And after collecting this data, we build an estimator for the non-quantum state, and we ensure that this estimator is pure. So when we have ensured this, for the remaining rounds, we just play this estimator as our action, because now our action set contains all rank 1 projectors. So this estimator is also in our action set. So yeah, here's a summary of the algorithm. Just 2 parts: the part of collecting the data from polyobservable measurements, and then here you just build the estimator and you just play the same estimator at each round. Yeah, just for summary of results. So we have the lower and upper bounds. We have that they match for the discrete case. So discrete case of actions. But we have a gap of d square for general bandits, so that they contain all rank for continuous action set with rank 1 projectors. So we have this gap of d square that I commented before. And then I think that the best open problem that we have is that in this pure state case, as I showed you before, when the actions are all rank 1 projectors and the environments are pure states, we have that the lower bound scales for the trace distance regret as square root of n, and actually the normal regret it's just a trivial lower bound. And we think that here we can find like better strategies for pure states that can beat for example, for the normal regret, it can beat the typical square root of n that we have in every example that we have studied. And actually, for this trace distance regret, the upper bound goes as n to the 3, but actually it's a very naive upper bound because this algorithm is not very adaptive. So thing to keep in mind is we conjecture that the regular regret for this case scales slower than square root of n, and actually we think that can scales just as a logarithm of n, because our trivial lower bound is constant, but we think that it cannot be improved, but we need to find this strategy. So yeah, I think that this was all.
Okay, thanks a lot for the talk. Are there any questions?
So I have a single question, comment.
Well,
okay.
I cannot hear you very well.
I have a question. I have a question. Can I make a question? So first one is you discuss the regret, but I cannot find the meaning of regret. Could you explain the intention of the definition of regret?
Sorry, can you type the question in the chat because I cannot hear the audio.
Hmm?
Oh, the meaning of the regret. Yeah. So, because the thing that you want to do is to, can you see my screen? Okay. Yeah, can you see my screen now?
Yes.
Yeah. So the objective of the learner is to find the observable that has maximum overlap with this quantum state. So as you see here, the regret is just the relative loss between the best thing that you can do, so the best observable that you can pick, and the observable that you're picking at round t. So what you want to do is to minimize this quantity, because if you match at round t, you are choosing the observable that maximizes this trace of rho OI, then the regret will be 0. So this is like the relative loss that you have at each round. So, and what you want to do is to minimize this, because as soon as you have like regret 0, the regret is constant at some point, it means that you have learned the best observable. So this is the meaning of this regret. So it quantifies the relative loss of this learning task.
I cannot understand. So what is A? A is what kind of set?
What?
A. What is A? Calligraph A. I cannot
A.
understand. Yes, yes. What is this?
This is the action set, so the action of observables. So it's just just an argument of the set of possible observables that you are quantifying this regret.
What is pi?
Pi is the strategy. So it's what is the probability distribution associated to the learner. So it's like the strategy that is following the learner to select the observable at each round.
Why this one can be considered regret?
Sorry, what?
Why this is regret?
Rigorous, you mean?
Why? Reason. Why this one is called regret?
Why is it called regret, I think?
Regret. Oh, okay. I mean, we have just taken the name from the classical bandit problem that quantifies the learning task. I mean, specific name, I'm not sure why it's, I mean, regret, because I don't know, in all these online learning tasks, you have these regrets that quantifies the relative losses between you are learning.
Okay, so in the interest of staying in schedule, I suggest we continue this discussion over Slack. Is there just a quick question by any other participant? If not, let's thank Joseph again.